Okay, let's start. I posted the papers for next Tuesday. So again, 5 papers. I think last time I'd said that we were going to do it this Thursday. I was wrong. So next set of papers is on Tuesday, next week. Also, a bit of heads up. So next week's Thursday, I'm on travel. So what we are doing is there is a lecture that my postdoc is recording, which is based on my own material, but this time we're also adding a homework in it. So what that lecture is going to be about is attacking control flow in software. So normally I cover that material a little bit earlier in the course, but this year I deliberately skipped it. But it's basically attacking software by exploiting vulnerabilities in it, or when the software gets infected by a malware. So it's basically what are referred to as exploiting bugs in the control flow, like causing an overflow of the buffer, crashing the stack, things like that. So it's a very important area, and in fact, when it comes to software, that's probably the biggest source of, that's the biggest source of the way things get hacked, if you may. So Louis, my postdoc, he's doing that, and as part of it, we are hoping to, we're still kind of working on that, little exercise where you will have to essentially hack into a little drone, into a drone in a simulator. So kind of the idea is mimicking this notion that can I remotely get into an embedded system. So anyway, so our plan is to actually record it and then release it. So next week, Thursday, there will not be any class, but instead you would be, so again, next week, not this Thursday, okay? Next week's Thursday, you're going to watch that lecture and do the homework. So just a heads up on that. For next Tuesday's paper presentation, as usual, as with last time, reviews via Gretschko. I've already created the homework there. Paper review assignment number 2, and also those of you who are presenting, kind of just send me the links by half an hour prior to the class so that I can upload. So anyway, so that's also, since next time we will actually hopefully have 5 presentations and no one drops out. So very important that you keep the presentation to the time limit. Okay, so last time we were looking at this whole notion that how microarchitectural state, that is all these hidden memories and registers, are left with kind of almost like crumbs of data when an application runs, and that can be exploited in nefarious manner. And one such thing was that we basically get the victim to affect the state of the cache, and then the attacker examines the cache, not the contents of the cache, because of course we can't read it, we don't have the privilege, but we can examine the effect of the data being present in the cache or not by basically seeing whether I can access, whether my access, which is on the same location in the cache, is quick or slow, and that would basically indicate whether that location in the cache was dirty or not. So we had kind of discussed that how you can flush the cache and then cause the victim to, let's say for example, put the data there, and if so, I seed the cache, the victim puts his stuff there, and then I would see a slow time, or kind of vice versa. There are different ways you can exploit it. And in particular, this is what gets exploited in these attacks, which originated this whole line of work called Meltdown and Spectre. One point which I didn't sort of explicitly made clear when I discussed Meltdown we are yet to discuss Spectre. So the difference between Meltdown and Spectre, loosely speaking, at a very high level, is the following. Meltdown happens when an application, kind of a nefarious application, either infected or kind of is seeking to essentially look into regions of the kernel memory, and because of the way many operating systems map the entire physical memory into the kernel memory, and therefore it basically can dump the entire physical memory. So Meltdown is about a malicious app peeking into the state of the machine that it would normally not have access to. Spectre, as we'll see, has a different setting. Spectre, there are two processes on the same machine. One is a victim process, one is attacker process, and attacker process is trying to examine private content of the victim process. Okay, and in particular, we'll see that Spectre requires that the victim process have a particular pattern of code in it, whereas Meltdown, and I'll kind of recap what I had covered at the very end last time. Meltdown simply leverages a feature of Intel processors in particular. So there is nothing, no code pattern required and all, but you need to be on that machine itself where you are running. Whereas with Meltdown, that attacker process could be a piece of JavaScript code inside the browser, for example. So you can mount those things to the browser. So anyway, so Meltdown is about attacker process or nefarious process on the machine, being able to examine memory which was normally not within its privilege, whereas Spectre is one process affecting another process, and in either case, it is not about any bug, but rather the way hardware works and exploiting that. So Meltdown, to kind of recall, really makes use of the following insight, that some processors, all Intel processors and some ARM processors, but not AMD processors, had the following characteristic, that when an exception happens, an exception refers to when there is whatever, divide by zero, access to illegal memory, stuff like that, then when what the processor does is, since detecting that the exception has going to take place takes a little bit of time, so meanwhile, for sake of efficiency, the processor is still executing instructions, and then it unrolls them once the exception is detected, but when it unrolls them, it only unrolls the effect which was there in the registers that are part of the instruction set architecture. It doesn't unroll what happened in deeper down, in particular what happened in the cache. So I talked about kind of what concepts of out of order execution, which basically means in modern processors, they continually kind of examine the set of instructions and they race ahead basically. And the idea is that these instructions you are racing ahead, when they write to registers, they are actually writing to some shadow copies. And the idea, and then at later point when we are sure that they must have been executed, we actually do kind of a commit to that. An exception I already talked about. So the insight was that architectural state is rolled back when we realize that the exception has happened and that the instructions we had raced ahead to perform shouldn't have been performed. Okay, so we roll back the architectural state, and actually, like I said, the way the rollback is done is not literally that you are undoing the thing, but rather, to begin with, you only wrote them in some shadow register, so you kind of discard them. But the content of the cache is not. So anything that those optimistically executed instructions that we raced ahead and did, if they affected the cache in any manner, that effect remains, and that's what sort of we make use of. So towards the very end, I'd walk through these slides, which is sort of essentially the idea is that we are going to invalidate the cache, and so everything is empty, and kind of the idea is that we know the layout of the programs and stuff like that, so we know where we map to. Some other things to keep in mind is that when there is a cache miss, So let's say I'm trying to read a address, read from some address, and it's not present in the cache. So the data needs to be fetched from the main memory. What do you think happens at that point? What all data are brought into the cache? So let's say I'm accessing a particular address. Is it just that address which is brought over?
No.
So
By entire cache line.
Entire line, exactly. So, and that's because when you're reading from DRAM, also you kind of read the whole thing in one go. So entire cache line is brought in. Okay. So that's an important thing, which is basically if I touch one byte, it's kind of the whole cache line is going to get impacted. Okay, but keep that in mind. So we invalidate, we basically flush the cache, and then at some point we cause the victim to load into some location in that cache, something which depends upon the secret. So in a sense, I cannot read the data that the victim wrote. That is not allowed. The processor will not let me do that, or the OS will, I won't have the privilege. But if what location is written to depends upon the secret, then by knowing which cache line is faster, which cache location are faster to access, I can basically have the same effect. I get to know the secret. And around that, and then kind of I probe it. So around that was the whole concept built. So kind of the idea is, yeah, I think we can ignore this. So the idea is, let's say there is a byte in the kernel memory that I want to read. Okay, I want to read the content of that, and remember, as I said, since physical memory is mapped to the kernel, so it could basically be something which is really, I want to read an arbitrary location in the physical memory. It works for Linux, works for Mac OS X. Okay, so now what is happening is that this RCX is a register which contains that address in the kernel address space, whose value I want to read, right? So RCX has the address, and I want to read the byte that resides at that address. Okay. RBX has the address where a probe array starts. Okay, so that's my own. Okay, and remember, we are the process which are behaving maliciously, trying to read into the kernel thing. So the attacker is this code, and the victim is the operating system, so to say. Okay. So now what we do is we say move into the lower AL, so which is the lower half of the A register. The value from the memory location pointed to by RCX, right? So it's indirect addressing. Okay. So now remember, RCX, the value in RCX is a kernel address, right? So of course, I'm a normal process. We are not allowed to read it. So we expect a exception will happen. Except prior to this, we would have flushed the cache. So we would have made sure that this stuff is not even in the cache. So let alone kind of figuring out that we can't read it. So the address is not in the cache. So all of these things. So this thing, it will be a little bit of time before it will realize, before the processor hardware will realize that there is an exception. So the exception doesn't happen immediately, and because of the cache miss, also this thing is going to take some time. So therefore, meanwhile, the processor will go ahead and execute the following instructions optimally. So now what's happening in the next instruction? Next instruction, what we are doing is that this RAX, we are basically shifting it left by 0xc. Now, what this RAX is designed, I guess prior to that, left hand side out here, is things are sort of zeroed out. So this RAX, it represents kind of the overall register. The effect of this is multiplying it by 4096 and 0xc. So c is what, 13, so you're kind of shifting left, so it's 13 times. So essentially what we are doing is we are creating page 4096 is the length of the page. Okay. So kind of the main idea out here is that we are creating an entry into the same page as what that kernel address resides into. Okay, so we are going to cause kind of the whole thing to be fetched in. So we are creating that address, and then we say that rbx plus rax. So rbx is the probe array. RAX is now designed to be an offset which leads me to that kernel address. Okay, so we would have initialized RAX accordingly so that the chip does that. So when we do this, this essentially reads the whole cache line around that target address, and in particular then we take the code word out of it and then we move it to RBX. So what's happening at this point is that the cache, that cache line would get impacted, whose value would now depend upon whatever the content of that particular address are. Okay. So this will go ahead, and then at some point exception will happen, and when the exception happens, it basically unroll these things, but the cache has been impacted. So which cache line gets impacted now basically depends upon what was sitting in that byte out there. And the processor, the way Intel processors work is the way their exception mechanism work is that they don't undo that cache effect, and then after that basically once the exception has happened, you can kind of go ahead and read this thing. And so you still have one other challenge, which is you have to make sure that when the exception happens, normally the process gets killed. So like if the exception happens and I'm doing all this game, then the process will get killed and I will never have the opportunity to probe the cache, right, to actually extract the data. And this is where yeah, I think I can skip through these things. Let's see. Yeah, this is where a few different things could be done. In some cases, you can actually install a handler. So the idea is instead of crashing, the OS will let your handler run, and you can do cache probing there and whatnot. You can also fork just before it. So there are a variety of ways you can basically. So you can fork so that the child gets killed and you survive. So there are a variety of ways they make sure that even though this exception is happening, either not getting killed or a clone of me survives, which can go ahead and perform the cache read. So we extract the information. So they are pretty, if you search on YouTube and all, they're pretty cool things that they show. Like, I mean, you're typing your password merrily, and this since it's getting mapped to a physical process, it can extract it. It can take the entire password thing out of password area of a browser and extract it. So works pretty rapidly in the sense that you can dump the whole physical memory at obviously slow speed, but still pretty fast. So in short, you can dump the entire physical memory through these games. Okay, so all you need to do is to have your process on that victim machine, but this process could be any app that you are downloading. I mean, that malicious app may deliberately have this kind of a code hidden in it, okay, to extract this information. So that's Meltdown, and there were ways in which people tried to cope with this, like when the bug was discovered. So like some operating systems allow for randomization of the kernel address space, so things are not precisely the same place in every machine, but turns out the options are not that many, so that is it's easily undone. Some other OS level mechanisms which also kind of help out in that. Okay, so that's Meltdown. Now Meltdown is obviously harder to do in the sense that I do need to get the malicious application on the target machine. So it could be an add library, somehow it needs to get there. More dangerous is an attack which we can remotely mount, right? I mean, cause the user or a device to visit a URL, and just by virtue of downloading a JavaScript or a WebAssembly code, we cause it to do nefarious things. So this leads to Spectre, which is the other type of attack which I had not covered last time. I stopped prior to this slide. And this one exploits conditional branch misprediction. So this goes to, again, another, so the previous attack was based on out of order execution. This one is exploiting another capability of modern processors called speculative execution. And intuitively speaking, kind of the idea is that when we are faced with a jump type instruction, then since it will stall the pipeline, so instead of kind of figuring out whether I should take the jump or not, based upon prior history, the processor says, let me go down whatever left path, okay? And if I'm going, hopefully I'm right, and if I'm wrong, then we can undo it and go down the right path. So that's called speculative execution, and in the processors are basically these things called branch predictors, which maintain some history about what was happening on that branch, and based upon various information, they kind of make this decision that which way they predict. Modern branch predictors are very good, routinely achieving 90+% type correct branch prediction accuracy. Okay, and in many cases they are basically little neural network or some other machine learning function. Okay, so that's what this thing describes. So now imagine if I am doing some sort of a conditional operation where the condition is something like this: x less than array1 underscore size, and let's say x I have and it's cached. And later on, we'll also see that a requirement on this attack is that x somehow should be under the control of the attacker. Okay, that attacker should somehow be able to influence x, and that means that x has to depend upon an input that the attacker is providing, maybe something on the command line or entered in a text box. Okay, so now imagine we are faced with somewhere this code pattern occurs in the victim process, and x less than array1 size, except that array1 size is not cached. So at this stage, the processor, this will take some time. So what the processor will do is it will race ahead, and based on the branch predictor, either make some decisions. So this is where comes another issue, which is somehow we are going to train the branch predictor to actually execute this next instruction. And that again can be done by first seeding a set of values to x which kind of bias, essentially kind of make the branch predictor decide that that's the right decision to go, this instruction. So let's say we have accomplished that. So now what will happen is that it will optimistically go ahead and execute this thing, and let's say we have this type of code pattern. Array1 index x, remember x we are controlling, multiplied by 256 for the cache line, and or actually I think it's distance into this, and then we index into another array out here. And kind of the idea is that the secret that we are after is really this which is contained in this array1. So we are going to see how that plays out, but the idea is that we go ahead in this branch. So and again, what this is again what modern processors do is that when they unroll from that incorrectly executed instructions, so we force it down a path which later on will turn out to be wrong. Then when they unroll, only the register values are unrolled and not the cache. So we see that story again and again, that cache is not rolled back. And we work of that. So in this particular case, after some time afterwards, this thing becomes cached, becomes available, and then the processor realizes that this condition is violated and that it should not have executed this. But already this execution took place, and in particular because it depended upon x, and so the state of the cache somehow now reflects the value of x, and we are going to extract that. So attacker chooses a memory buffer, which is of the same size as the cache line. Attacker then accesses all the lines, which is the same size as cache. Attacker accesses all the lines, so attacker basically arranges that the entire cache is now filled with the data that it provides. Okay, so now the whole cache is filled up with attacker's data. Then victim executes. And the victim will execute, and somehow we, by looking at the open source code and all, we know that the victim has this kind of pattern. Okay, so the victim executes, and when the victim executes, it's going to put some of its data into the cache, and in the process, it is going to be evicting some of the places where originally the attacker's data was residing. Okay, so these entries become are now hosting the victim's data. And the idea then is that the attacker then measures its own buffer, which is mapped into this place, and see what was, which of the cache lines are seeing a bigger delay, and therefore it would know that those are the places where the victim wrote something which depends upon X, and therefore we can reverse enforce that X. So in this case, kind of key requirement is that, so firstly, attacker and victim are two separate processes, and the other thing is that the victim must be executing some code pattern like this, but it turns out that these code patterns are fairly common, but and they're perfectly fine, there's no bug in it, but if they exist, then any process with such a code pattern is vulnerable to an attack by any concurrently running thing that exists. So so how does this work under the hood? Then a little bit is the following. So let's say there is array 2 out here. There is this is the base of array 1. Remember, the code looks like this: if x is less than array 1 size, int dummy equal to array 2, index into array 1, 256. Okay, and remember, our goal is to read something something in the victim process. So let's say the victim byte is out here. Okay, this red color thing. So that's what we want to read. It belongs to the victim. X in this case is the distance from the base of array 1 to X. So I'm going to systematically read some secret out of the victim process, in this case X, and I'm going to design X such that it represents the distance from the base of array 1 to that byte. And then, since I'm somehow controlling X, presumably through some command line input, so I'm going to make sure that X takes that value. And now what will happen is that when array 1 of X is done, then it is going to fetch the victim byte, and then it will try to access, and remember, array 2 is part of the victim process, so it will speculate, because it's speculatively executing, it's going to try to access this. So it's going to try to access array 1, so array 1 of X is this guy. It's going to try to access array 2 with this value, and then the corresponding cache line will get impacted. So essentially, we are coaxing the victim process to now go ahead and do this access, which it can, because X was available to it, so it can race ahead and do this part while it is waiting for array 1 size to be figured out. So long story short, we can, as long as that code pattern exists and we can influence X, we can read that necessary byte. Okay, so I'm not going to go into details, but it can basically read the content of X. Yeah. It is for the cache line, 256 bytes. It is bringing. So
you just want to reach the victim byte, but if you do the scaling, it will reach 256 bytes, 256 addresses ahead of the victim. So that
it will.
if the distance is
so content of the byte out here. I think the array2 data type is probably designed this way, that it is doing this so it's a struct, it's not, the array2 is not a byte, it's an array of cache lines. Okay, so this particular one is more dangerous because the attacker could basically be a piece of code which your browser is running as a result of some JavaScript. So people showed when it came out that you visit a website and the JavaScript code can merely extract information from other processes on there. Since then, there has been a whole industry of all sort of other microarchitectural attacks that people have discovered, not just through cache, but other things. Even like modern processors have capability of running multiple threads in hardware. It turns out that there are timing attacks that can occur because those threads share certain common resources. So it's called port smashing attacks. There are a whole bunch of things which have emerged, and for some of them, there are basically no solutions at present. Okay, in the sense we are basically susceptible to them, and kind of the answer to some of them from the processor companies is that if you are sharing hardware, then be careful. In the sense, don't share with those that you can't trust. If you are running virtual machine on cloud service provider, then two virtual machines can steal data from each other. The hypervisor, which is under the hood software, can steal data. All these combinations are sort of coming out, and every security conference over the past 24 months have several papers on this topic. Okay, so yeah, I'm going to skip this because it covers. Okay, so a general defense. Again, not going to gory detail here, but just show you one particular picture. Okay. So some proposals, and this is something out of University of Illinois, where basically what they do is that next to the cache, they also have almost think of it like a temporary cache. So the idea being that we are going to corrupt the state of the cache only when we are sure that it needs to be corrupted. So this block called SP is basically kind of envisioned as almost like a scratch pad or scratch buffer in this case. So when we are doing things into the cache, but doing so because of speculative reasons, then we are going to put stuff there, and only when we are sure there was no exception, and only when we are sure that we took the correct branch, that we are going to commit it. Okay, so essentially kind of the cache gets modified. This is sort of a general defense, or at least that's the claim, because anything which depends upon polluting the cache and then measuring the timing and all can be solved by this approach. Of course, the issue is that it adds additional memory which you could have otherwise used towards performance by having a larger cache. And the other thing is that, of course, it's only when the next generation of processors come around. Okay, and given that processors and all are usually on a multi-year design cycle, I mean, sort of the processor whose design they start today is aiming for something 3-4 years out. So it's not something that became available easily early on, and then of course it doesn't solve problem of processors already out there. So a whole bunch of issues, obviously, so not ideal, but there is no choice. So one thing which has emerged is that there are all these sort of things which are perfectly fine in terms of their architectural behavior, but which leak information have emerged, and the processor vendors are kind of fixing it. And essentially they exist in every processor, some variant. I mean, not every such attack applies to every processor, like the exception one was only for the Intel processors and some ARM processors, whereas the other one was applicable to all of them, but to varying degrees they exist. And the main culprit in a way is that when we are sharing things. Okay, none of these things would be an issue if we were to not intermingle stuff, but in many cases you don't have a choice. But if you're kind of like a super paranoid entity and running stuff on some cloud service or something, you absolutely have to insist that there is nothing else co-resident with your stuff. And if your critical piece of software is going to reside together with something non-critical, then you are taking risk. So in more sensitive settings, military and all, they kind of think of their computing platforms as kind of a red part and a black part. Black part is safe, red part is not. And any communication even between them and all is kind of at every level, physical and logical protocols and all, is severely firewalled, because all these unintended leakage that happen, okay, are pretty risky. So very, very careful and enforced separation is basically the way out. Okay, so these microarchitectural attacks, I mean, they're, like I said, they're code snippets and all. You can download and run it and try them out. They do depend, one thing they also depend upon is the ability to measure time, right? Because we are doing the cache timing thing. So one way out is to prevent applications from measuring time, okay, or measuring time reliably. So remember, the most dangerous version of these attacks was the second type, where a remote entity could mount an attack. So you could imagine that for JavaScript scripts, we can make sure that the timing function is very noisy. Okay, so in a sense, when a JavaScript queries the system for time, instead of reporting a true high resolution time, we kind of just add noise to it. And this idea that timing, letting applications have precise timing information can cause security issues and all, has been around for a while, in the sense that there were instances. So there's a classic paper from 1990s which basically introduced the concept of fuzzy clocks, and kind of the idea was deliberately that if you don't trust something, don't tell them the true time, because there are many other attacks which also depend upon measuring time as a side channel. So that's a possibility. The instruction which I had shown last time, RDTSC, read timing something, in Intel, that is actually an instruction which an OS can disable for a process. So an OS can set that user space applications will not have access to that instruction. The problem is that so many things depend upon, so many good things depend upon precise timing, like profiling and stuff like that, that simply a blanket strategy that applications will not have access to such an instruction is kind of tricky. But you could imagine that you can use access to precise timing instructions as potentially a way to identify suspect code, okay, because if they are dependent upon this, so you could do kind of binary analysis. That is, if you, when the application being installed, you can imagine sort of going through it and then identifying that are there pieces of code which are going to result in some nefarious behavior, or even perhaps do it at runtime kind of thing. So there are other defense mechanisms, but none of them again are perfect, and they also come with overhead. So that's where kind of the state of affairs is. I think this remains kind of a super active area of research, and both attack and defense mechanisms keep coming out. Okay, so switching gears a little bit further, the next topic that building on this theme of kind of architectural thing and all is that so hardware introduces these vulnerabilities, but hardware also provides tremendous amount of support for security. So I wanted to cover a little bit of that, and some of these things are seen in embedded side also. Some of them are kind of more for normal general purpose processors. So how does hardware help in security? So one thing which I've sort of loosely mentioned before, and you will see more in that recorded lecture that I'm referring to, is that enforces a separation between kind of tries to establish these privilege modes. So all processors almost, other than the teeniest microcontrollers, they have some notion of privilege with which the software is running. So in Intel processors, it's called rings. So ring 0, 1, 2, 3, like that. And the idea is that we basically create a hierarchy. So if a software is running at a level where, which is less privileged, then it will not have access to some resources, and the only way it can get access to those resources is by basically creating a trap or a system call to a more privileged piece of software. So the idea is that hardware enforces isolation in this mechanism, and thereby we can make sure that an application, a normal application, cannot corrupt the operating system or peek into the operating system and thereby cause issues. And if we can, and if the only, and if furthermore, if we can ensure that two applications cannot talk directly to each other without going through the OS, then in theory I have kind of perfect isolation, right? Two applications cannot mess with each other, and the application cannot mess with the operating system. So, this in a way results in a platform where we trust the operating system and we trust the hardware, right? So hardware is working correctly and the operating system is behaving nicely. So that's one role, and all, like I said, all processors above some level of complexity provide some notion of some form of kind of privilege structure. Another one which you see quite a bit in modern processors is support for cryptography. So you see cryptographic accelerators and you see random number generators. So 2-3 weeks ago when I talked about crypto, I had mentioned that how Intel processors has special instructions to realize AES, which is the crypto standard. Many embedded processors have it. If you look at data sheets for many embedded processors, oftentimes they have a crypto accelerator there. Okay, so typically as part of the communication subsystem, because many of our communication standards like Zigbee and Bluetooth and all, they need AES. So they exist, either special instruction or accelerators in radios, but they kind of exist. In some processors, you will even find support for elliptic curve cryptography, which is used for public key cryptography. But in recent years, some additional roles have emerged, and the whole idea is to create within the processors kind of a special module which has a higher level of trust in it somehow. So it could be, so it's often referred to as secure hardware enclave or trusted computing bases and all, but they kind of allow for a litany of functionalities. For example, maybe they can store keys or they can help establish keys. So for example, the processor may come built in with a public private key pair. The private key is inside this secure enclave, and there is no way you can look inside it. In fact, they literally design it to be non-tamperable at a physical level. Another one is to store other secrets which you might be worried about. So, like those of you who have iPhone, if you know, often when you start up and all, kind of firstly when it does your fingerprint or Face ID and all, those things are stored inside the enclave, and as which Apple has created this security chip, and therefore whenever you restart the phone and all, you have to re-initialize it. You can't get information inside the enclave without then retyping your password. Okay, so there is information in there. Another one is timing. So I'm sure if you're like me, I'm sure at some time or the other, maybe you have tried to misuse a license by turning back the clock on your computer. At least I have. But it doesn't work with these modern machines because they do not allow time to go back. So deep inside, some of these things are basically the ability to maintain clock through power cycles, and something which will not go back. So essentially a clock which can't be turned back, and therefore for digital rights management, it becomes a great thing. Also, being able to uniquely identify hardware. what makes my iPhone and your iPhone of the same model different? Well, if two devices are starting out identically, like literally the same part number, okay, then how do we make sure that they are distinct, right? I mean, let's say I buy 10 of them, there has to be something distinct about them and be distinct about them in a very scalable manner, right? I mean, imagine it's not that every time a chip is made, someone is going to go and enter some number in them, and even if they do, where is it going to get stored? So it has to be something which is intrinsically part of the manufacturing process. So kind of like a digital fingerprint. So a concept which I want to talk about later called physical unclonable functions. Essentially the idea is that we make use of physical properties of the hardware, okay, to essentially associate a unique ID which cannot be figured out. Okay, that's the thing. Like you can query it many times and all, but there is a deep down there is some sort of a unique fingerprint which you can't learn, can't replicate. Okay, so can we achieve something like that? So you will see kind of variety of terms used: secure enclaves, trusted computing base, TPM, trusted processing modules, which is kind of the early version of these things. It's used in PCs, and you can kind of buy separate TPM modules on Amazon for like $2-3 for your PC board. Kind of didn't do very well, but like Apple's Secure Enclave does a terrific job on it. It's basically kind of the whole privacy and kind of security mechanisms are built around that. Everything kind of on iOS and Macs too now traces it to that little piece of thing. Whether your operating system is been tampered with or not, whether there's an authorized piece of hardware, software or not, whether if you replace a part on your phone, whether it's a valid part or not, all these things ultimately, directly or indirectly, rely upon some sort of privileged information which is inside that enclave. So that's kind of the concept. Okay, so let's start with random number generation first. Okay, so as we discussed way early, random numbers play a very important role in crypto protocols, and if they are guessable in any manner, then basically your protocol will get broken, right? So we need good random numbers. Moreover, we need lots of random numbers, right? Because if we are going to be encrypting lots of traffic and stuff like that, we need to have like a good supply of random numbers. And I had talked about like what does it mean for an algorithm to act as a good random number generator, secure random number generation. So RNGs are at the heart of crypto. You use them for testing, gambling, Monte Carlo simulation, for reCAPTCHAs, all sort of other stuff also. Of course, not all these applications have similar levels of requirements. So for example, there's an organization called NIST, National Institutes of Standards and Technologies, and they have something called a NIST battery of test for randomness. And they are a good test for statistical randomness, but they are not necessarily secure in the sense of what we kind of talk about. They basically look at average and variance and stuff like that, and kind of you need to pass them. So properties of RNG, they need to, you can think in terms of their predictability and uniformity. So the state of the art RNGs, they fall into kind of three categories. So one is we take a random seed, and then using one of those secure random number generation algorithms that we talked about, we amplify that, and then we generate the stuff from that. The problem with that is that if the seed entropy is limited, then that might be very easy to predict. Okay, so you essentially the only true source of randomness out here is a seed. Everything else is predictable after that. On-chip RNGs, in this case, some physical thing is used to which we know from physics has randomness properties. So, for example, thermal noise. Could we exploit that somehow and extract this entropy? A couple of problems out here. Firstly, just because something is unpredictable by you or by a mere human doesn't mean that it has its unpredictable period. The amount of entropy in some of these things might be quite limited. So just because something looks wiggly doesn't mean that it has lots of randomness in it. So one needs to be able to quantify how much entropy exists and not exceed that, because otherwise again you run into predictability. Moreover, there is another challenge with these physical ones is the following. Even if they have, let's say, requisite amount of entropy, there is no way for you to audit them, like what exactly happened. There is no deeper insight into it. I mean, we hope that the thermal noise has adequate entropy, but we don't know for sure, right? How many bits of entropy are there. So that's the drawback. And the other thing is, because of the limited entropy, the rate at which you can get random bits out of it is going to be limited, which often doesn't suffice. So more generally, what happens then is that systems use a whole bunch of sources of entropy. So kind of there are lots of little sources that exist in a computer system, which provide some randomness, okay, and you kind of combine these together to get more entropy. So for example, keyboard interrupts, okay, like when I type on the keyboard, the timing of that, or maybe the duration with which I'm pressing the key, or for that matter even, so let's see, which key I press is probably not terribly random, right? I mean, there's probably some randomness based on the text I'm writing, but English language is pretty predictable, right? Timing, maybe some more predictability, some less predictability, but still sort of, if you look the distribution across humans, it's probably not a whole lot. But each one of these things give us a little bit. So keyboard is one, network packet arrival. So if you observe whatever, if my laptop were to simply observe the traffic and all going around, there's probably some randomness that you can extract from that. So a lot of these things are possible for any computer system or embedded system to extract. Okay, noise and sensors, so like taking that, other things that kind of vary, the sound that it is hearing, all of these things have some potential randomness. You combine it, extract some amount of whatever randomness you can, and then use the algorithmic approaches to amplify it. Yeah. So if you look at like go into Linux and go into the devices and all, you would see that there is a /dev/random or something like that, where you can actually read and get a random number. And what the system does is it goes into the pool of random bits it has been collecting from all these physical processes and then give you the next bit out of that. Or there might be an algorithm layered, which is you're seeing the output of that. So yeah, I've kind of listed these things: keyboard, mouse movement, IDE timings, fan noise, hard drive noise, audio data, video data, network interrupts, microarchitectural state, all these kind of things. And then sometimes processors also have dedicated hardware random number generators, so like Zener diodes or stuff like that, some sort of a physical thing on the chip doing that. Servers face a different problem, and so do embedded systems, which is they do not have access to some of the sources that you readily can rely on your laptop, and also like key and mouse don't exist on servers. Now, one thing that happens is that if the system runs out of randomness, like a server system, then it can't communicate effectively, right? Because you may have an SSH session and you need the next key, and well, you don't have. So if the system runs out of random numbers, then the processes have to basically wait until they can actually until the system collects enough randomness. So as a result, the speed of your communication can get degraded, because the rate at which you are communicating has to match the rate at which you can keep the randomness supplied for it. So it's kind of an interesting thing, which I guess most of the time we don't even know what is happening under the hood, but you need this supply of random bits for secure communication to take place. Embedded systems have issues also when it comes to gathering this enough randomness. So part of the challenge out here is that they are very simple devices, so they are resource constrained. So if you have random number generators which are going to take watts of power, you can go on Amazon and kind of search for random number generators, and you'll see that there are boxes sold with a output wire, and you can get random numbers out of it. But of course, not a very viable thing for these devices. The challenge is, let's say you buy a bunch of Arduinos and you boot them at the same time. So now think about the problem at hand. How would you, if those devices are identical, same model and all, and you booted them at the same time, the powered at the same time, their state is going to be exactly the same. So if they were to try to come up with their first key, then the key would be exactly the same. So how do you make these otherwise identical devices somehow differ, right? And that's where the random numbers have to sort of come into play. So these are devices which are very simple, and you might say, okay, maybe they can wait and sort of collect environmental sound and stuff like that. But what do these systems often do? They come up and they have to connect to the network. They have to maybe contact a server. Well, to contact a server, they need to generate, do an SSH or VPN. For that, they need some random numbers. But you have just booted up. Your state is highly predictable. So where do you get those random numbers for, right? So even in the early stages of the boot process, we need access to these random numbers. As a consequence, what happens is that there is oftentimes you would see very weak initial keys being used. I mean, versus obviously, like they'll manufacturing time, they will just decide upon some random looking string and say, look, I'm going to just burn it in, and we are just going to use that, and no one is going to be able to figure out what it is. After this course, hopefully, if you ever design thing, you will not make that mistake, because anything which is sitting in your device can be extracted. Okay, so that's not a very safe way of doing it. So having good random number generators, even in these simple devices, is important if they are going to talk to anything else, right, outside. So, kind of long spiel on, we need a good supply of random bits. In Linux, there are these sort of OS deep down, with the help of the processor and potentially other hardware, kind of collects this randomness. Now it has to expose it to the applications. So you have /dev/random. It is very high quality, good for a one-time pad or key generation, so you can kind of use it for that. But it is entirely based on collecting information from these different sources, and once it is empty and you try to reach /dev/random, then you'll have to wait until the system has collected. So for example, like I said earlier, for servers and all, this could be an issue. /dev/urandom is another device in case of Linux, and this one is non-blocking, and it has an unlimited supply of randomness. Of course, it is now no longer true physical randomness. Okay, so in this case, they use a particular algorithm called ChaCha20, and it basically takes that physical randomness it has been collecting, and then algorithmically amplifying it so that you have the illusion of infinite supply of randomness. You never run out of it. You just go to dev/urandom, and for most cryptographic purposes, it is sufficient. Okay, but no one truly knows. Okay, in the sense that these are still algorithms. They still probably will have some pattern to it, but so an attack may exist. But generally accepted to be a good enough thing to have. So if you are NSA, you'll probably going to rely on some hardware things which are supplying you sort of quantum randomness and stuff like that. If you are ordinary users, okay, these kind of things are okay until they get broken, and that's the challenge. A lot of things in crypto are based upon supposed hardness. Okay, so this is again one of those. Okay, so dev random and dev u random. To supply these things, so as I mentioned, there is a whole bunch of sources of physical entropy that exist. So those sources are combined, and then there is some particular algorithm, which doesn't really matter what it is, URL and it is, which kind of pulls them together. Okay, so you basically take these physical sources, you pull them together, and now you have that pool of randomness. There is kind of, you can try out some of these cool commands. So like if you want to look at how much entropy your Raspberry Pi currently has, you can do this cat and you can look at how many bits of entropy currently the system has. Okay, and then of course, as processes use it for VPN connections and SSL and whatnot, that depletes. On the other hand, as it encounters more network traffic and stuff like that, or other user input, it builds up. If it results in anything less than 100 to 200 bits, that means you are close to exhaustion, and then your system can slow down in terms of its ability to communicate and whatnot. So one needs to have that adequate supply. So that leads to that, can we just not put hardware units which can give us lots and lots of entropy on demand, right? So and indeed sort of that has begun to happen. Many modern CPUs and boards do feature integrated generators. They provide high quality, high rate random numbers to operating systems, and thereby kind of to rest of the system. So there are many different ways. There's some pretty cool work in right here in our department, in EC department. Puneet Gupta, Sudhakar Pamarti's group, they are using some properties of magnetic MRAMs, magnetically based RAMs, which provide some cool randomness properties and make for very efficient random number generators, and you can have many of them on a chip. Okay, so you can have many sources running in parallel. So that's an example. So on Linux, these are exposed through a device called HW random for hardware random. Intel on its processors has on-chip random number generators, and they have corresponding instructions, read rand and read seed. These are kind of slow instructions. So read rand takes 110 nanosecond. Or roughly close to 500 clock cycles. So what's happening internally is it's probably running some algorithm on top of kind of the physical things. There are always lingering concerns about some of these things. Are there backdoors? Just imagine if NSA has convinced Intel to compromise that random number, this instruction on all Intel processors, then you have a systematic backdoor everywhere. Okay, and no one knows. Okay. So these kind of things are always kind of out there, and potentially with valid cause. I mean, essentially the supply of processors on the planet is mostly governed by one country, right? So no valid concern. There are so-called true random number generators. So these are boxes of hardware or boards or chips that you can buy. So they rely on kind of thermal noise, clock drift, kind of things, photoelectric effects, quantum phenomenon, things like that. So anything which at the physics level, because of Brownian motion or quantum states and whatnot, provides some assured physical basis for randomness, these things try to exploit. So many of them are quite costly, but many of them are also very affordable. So you can buy them for your Arduinos and Raspberry Pi hats with random number generators. So one can kind of use those. Sometimes they are USB connected. So I've shown some example. They are good in the sense that they provide close to 1 bit of entropy. So when you read n bits, you're getting kind of random pretty much, but it's usually a little bit less, so you have to again kind of build upon that. So this one is called 1RNG. It's an open source design. It makes use of an avalanche diode thing, and so you can verify the design, you can build your own. It looks like this tiny little device. Okay, so these things exist. Now, what are some of the other ways you can generate randomness in hardware? So here is one example. So look at a circuit like this. So I have inverters in back to back, right? So a ring of inverters, and it's going to settle in some state, right? I mean, if ignore let's say what I do is a clock tick comes, and so clock tick is feeding to both of these. When it goes down, then it's a system which is initially both are charged up, but that is an unstable state, so it's going to settle into something. Okay, and which state that it settles into is going to be driven by kind of some relative clock timings. It's going to be driven by kind of the tolerances and the sizes of these things, and also kind of eventual state has some randomness into it that you can exploit. So usually these kind of hardware tricks where kind of uncertainty comes from variety of factors, temperature is going to affect this, all of that, you make use of this. So so essentially we deliberately move things into an unstable state, and then we let it settle, and then the state it settles in, it gives us something. You can combine a whole bunch of these to get sort of more bits. There are federal standards which dictate sort of the acceptable random numbers, and again, if you are sort of designing something for that, then you have to make sure that not only you're using a good crypto algorithm, but also that you are using a good source of random numbers. So one challenge that exists with embedded devices is that some of these sort of sources of some of the good random number generators are often not they're either too high power or too large or whatnot, so they are not quite sort of acceptable for this. So so what can one do? So one, again, very tantalizing thought is, we learn about pseudo random number generators in a lot of our COM courses. Can I just apply them? Linear feedback shift registers and all. So essentially, don't. Okay, I think the second time I'm giving that message. Those algorithms, while random for purposes of typical communication needs, are not random from a perspective of security. Okay, so we shouldn't use those. If you are lucky, your processor may have the random number generator, in which case you should use that because they are providing you some access to the hardware thing. Again, as I mentioned, that the only risk you are taking out here is that if there is some government conclusion, then we are in trouble. So but the challenge is that these are non-auditable. So okay, so what does it take for a good RNG for an embedded system? Has to be low power, ideally on chip. Low power should not be adding, let's say you're talking about microwatt or milliwatt regimes. Should be low cost, should be very small, should be auditable, so that I can see if things are going wrong, what is going wrong. It should be insensitive to environmental factors. So it should not be the case that if the temperature changes or something, randomness, the entropy changes. It should be fast, so that it can give me a supply of random bits, and it should be truly random. Okay, so that's the long list of requirements that one has to do. So what happens now? Well, Um, very intuitively, I need to have some source of noise, which gives me the randomness, and then I need to have some sort of a conversion circuit, which gives me bits, which have all those properties, and it's kind of this hardware has all these properties. So we need some physical source and some circuitry to make this happen. So can you think of what so what kind of noise sources can we use on a circuit? Hmm? Yeah, but where would it come from, right? I mean, you're designing a chip, has to have or whatever a board. You have to have a source.
You can have an antenna, and then that can pick up all the radio noise that's around us.
Oh, great! So I will put your system inside a shielded box and break it. Doesn't work, right?
Analog signal that is there. So before the analog conversion,
No, so you need to think of components which intrinsically have noise in it, right? I mean, we deal with noise in circuits all the time, right? Noise here is going to be your friend.
yeah,
Maybe raising the jitter of a pulse generator. I don't know, the jitter between pulses.
So jitter in clocks, right? Because deep down eventually, right? I mean, those oscillators going to have some jitter. So phase noise, basic kind of thing. So you can extract that. Where else you encounter noise?
The startup state of the memory.
Startup state of the memory. Actually, so I'm glad you mentioned it. So it actually turns out it's not that random. Okay. So yeah, your intuition is right. One would think that, so it turns out, I mean, I'm not covering in this course at all, but people have shown that the startup state of even DRAMs, which are the leaky things, they preserve their state for hours. Okay, so you can power your system down, and because they have capacitances which basically don't leak away, so okay, so yeah, with a huge caveat, okay, that one has to be careful. So long enough time and all, absolutely, but otherwise one got to be careful there. Yeah. Huh? Resistor. So what about resistor? Okay. Yeah, I mean, if it's a pure resistor, then not a noise, but so it's not clear what's the obvious source of noise out there, right? I mean, see, remember, noise is different. So I grant you that if I purchase 10 resistors from the exact same part number, they will slightly vary, right? I mean, that's it. But that's not noise, right? I mean, that's a bias that each one of them have, and then once we are done, we have it. It's also true that the resistance will change with things like temperature and all, right? So there is some degree of unpredictability from that, although you could argue that if you were relying on that, then I'm going to measure the temperature and then try to break your system, right? So that doesn't quite work. So there has to be some other intrinsic randomness which
special kind of filter, either a very low pass or high pass, and use that signal for just measuring it randomly.
how?
So
Yeah, so I see where you're coming from. You're saying, look, there's always noise and all, and I can focus on, I mean, I can amplify it and then filter it or something. You could, but you still need the source of noise. What other sources of noise are here?
What the noise source from the tube light?
Yeah, tube lights, AC, this kind of thing. Some of them will still have predictability though. So, I mean, this is where you also have to worry about what does the adversary know, right? I mean, if the adversary adversary knows obviously what the design of your random number generator is, but if they're physically co-located, they have access to the same source, right? I mean, so the bad thing about AC signal and all is that not only can I read it, but so can the adversary. So it doesn't make for a good design. On the other hand, if you are worried, If you're protecting against a remote adversary or an adversary which will try to break it later, then it's an acceptable thing to have. Okay, so let's see how this group. So this is a paper I kind of picked up just from 3 years ago, just to go on to show that, I mean, people still are continually in the hunt for it. So it's a paper out of Stanford. So choice of noise is critical, as we see, right? It should be probabilistic noise, it should be large magnitude, it should be auditable, and it should be cheap to implement, right? I mean, all those things that we want. So what these guys did, and now I think many of you will probably be more well versed than I am, but they basically make use of a reverse biased avalanche diode, okay? And essentially in the diodes, inside their electric field, and the electrons move from it. What apparently deep down happens is that under certain conditions, when the electric field is of certain critical magnitude, then these electrons kind of bump off other electrons in the valence bands, and there is this sort of effect called avalanche that happens. And the resulting avalanche current is probabilistic due to, at the quantum level, due to the randomness that exists, and its variability can be basically thought of is the noise out there. So essentially in this case they are making use of an underlying quantum phenomenon that exists in this class of a circuit, and then they are going to amplify it. So the circuit is super simple, avalanche diode in a reverse biased kind of a setting, and then they build on top of it. So they have a reference voltage. They are comparing the current they are or voltage that they are seeing against that, and then they feed it into a comparator to get the bits out. So the challenge that these guys in this design is that they need a high voltage, so they need kind of a supply which boosts things up, and then you also have other problems that you encounter about it. So they kind of go around kind of creating a more sophisticated circuit. I'm going to skip through all of this, but basically kind of point out that this is one design which kind of they basically built it for very tiny devices. They took care of a lot of other issues like making it robust to external sources of noise and stuff like that. But their basic design is two noise sources fed from the same power supply. They compare and then they send out generate the bits this way. So this circuit is called Lampert circuit. There is a startup apparently which kind of makes these things, but entropy of each bit in this case is more than 0.9. So effectively for every bit that you are reading, you are really getting 0.9 or so bits of entropy. Some assumptions, and this is very important within every RNG, is physically secure, and because if the adversary is if you have deployed this thing and the adversary has physical access to this, then the adversary can easily begin to mess with these lines and all, and begin to kind of affect the random number generator, right? So one has to be very careful that what kind of adversary that we are kind of talking about. So yeah, so that's the this particular circuit. You can buy it. It's a very tiny little thing which works great for embedded systems. Okay, let's see. Okay, so next thing. So RNGs play an important role. Crypto we kind of talked about earlier, but we still have this need for like secrets within the platform. What can we trust, right? So thus far we know we can generate good random numbers. We know that we can efficiently do good crypto algorithms, but there's still ingredients missing, because what part of our system can I trust? So can I trust the hardware? What in the hardware can I trust? Can I trust the operating system? So ideally what you would like to have is, instead of trusting many different pieces, there should be one root of trust, and everything else that is built upon top of it. So some minimal part in the hardware that can be secure, can be trusted, maybe that is where ID is stored, or that's where the keys are stored, and we kind of make sure that it is safe and all. So that led to, I think almost 15-20 years ago, something called Trusted Processing Module, or TPM. And so this was the first attempt by the PC industry, the computer industry, to create kind of a secure module which your computer would have, and which provides certain functions and keys associated with security. So think of it like a processor which is adjunct to the main processor and is providing all these functions. Computer programs can then use the TPM to authenticate, do other things. So each TPM chip, for example, has a unique pair of public-private keys when it is produced. So, and then TPMs themselves are designed so that they are non-tamperable. No one can go and peek inside and look at what the keys are and all. So that's kind of the idea. And the implementation-wise, they are discrete. They are separate from the CPU. So essentially, you have to assume that the communication between the CPU and the TPM is going over wires on your board, and an adversary can intercept and monitor it, right? So somehow you have to make sure that things work over as well. So that's a more common one. More nowadays, oftentimes what we see is in the keys, these trusted, they're called trusted enclaves, when they are sitting on the same chip. So in case of like if you go to Apple's website, when they describe their A-series processors, part of the A-series processor is their trusted enclave, okay, and that's on the chip, okay, and again, internally, usually these things themselves use some microcontroller or something, so a lot of it is software, but in the PC industry, I mean, if you just go to Amazon, you can see that you can buy these TPMs. They are just these discrete modules, and in your motherboards there is a socket where you can plug the TPMs in. But more on the phones and all, you see kind of on-chip stuff. So what do TPMs have? So first thing is they have a random number generator using one of those things that I kind of mentioned. Then they will have some mechanism, some sort of an API by which you access, through which you can get cryptographic keys. So because that we need to have. A very important property which we'll talk about later is a concept called remote attestation. And what it refers to is the following. Let's say I installed some devices out in my organization, and I'm worried about has someone tampered with it. So can I remotely verify that the hardware and software on that device has not been tampered with? Okay, so let's say we don't worry about the hardware tampering for a moment. Let's say we only worry about software tampering. So in a way, basically what we're saying is that, okay, when the device boots up, is its code the one I shipped? And later on, at any given point in time, I should be able to verify that some malware didn't go in and modified the code, and the code is no longer correct. So, so how can we do it? Well, so one way we can do is the following, and still not the complete story, that remember that somehow if we can take all the configuration information, so like what peripherals are there, stuff about the memory, the code which is there, and we kind of take all that information, all that configuration information, and create a secure hash function out of it. And then we are going to put that secure hash function inside the TPM. And then when the system starts up, it will look at the configuration and will compare it and compute the hash over it and then compute the hash. So it's much like the message authentication code that we talked about way earlier. In this case, it's the authentication of the whole system. So like for example, Apple, I recall last year had gotten a flag over the issue that if you get your phones which have fingerprint sensors repaired at with third-party components, then the operating system will reject it because your authentication mechanism, the fingerprint reader, is not validated by Apple in that particular case. So that's an example where it's checking for the configuration, and if the configuration is not right, then it's going to reject it. If this is, you have to make the decision what part of the configuration need to be trusted or not. So clearly something like, if someone replaces the Face ID camera or the fingerprint reader, that's more troublesome than, let's say, some other parts of the system. But maybe even other things like if you're replacing, let's say, the DIMM in your PC, you got to be able to trust it because every piece of data hits there. So what to trust or not, of course, is a system designer decision. But what's happening out here is we're taking all that information and we kind of store it, and then anyone who, so there are a couple of ways you could kind of imagine something like this being used, right? One is this information gets stored inside the TPM, and we know that by design TPM is non-tamperable. And what will happen is that the system will boot up only if the configuration matches what is inside what we have stored. So it's very similar to what happens with our Face ID and fingerprint, which is when you register the fingerprint, then a hash of it is taken, or a hash of the key features is taken, and that's put inside the TPM. Later on, when you put your fingerprint or put your face in front of the phone, then the same hash is computed, sent to the TPM, it compares the two and gives you an answer, yes, no, and then based upon that, kind of it lets you in. So, so that the other way you can imagine using it is remote thing, right? I can ask one of the sensors in my organization, prove to me that you are okay. Okay, so what will happen is somehow we are going to engage in a protocol. It will verify to me that its configuration matches what at manufacturing type I had registered. So the idea would be when I'm installing these things, I'm going to put the hash of the configurations with me, and then I'm going to kind of ask for that. So, so that's one. Final one is that this concept of putting small amounts of data inside the TPM. Okay, so you can encrypt and essentially seal the. So you can do some of these functions where you can put secret data inside it, or you can ask the TPM to sign it. So the TPM, you can send the data to TPM, the TPM will sign it using the private key, and now it has basically, or encrypt it using its key, and that way you have something that cannot be tampered with. So essentially you can show that it could have only come from the this device with the TPM. So lots of these functions TPM provide. I think I also, if you look at this picture, it also has a whole bunch of hash storage and hash and all. I also previously mentioned that it maintains a clock which cannot be turned back. Okay, it's not a high resolution clock, it's a very low resolution clock, but it's designed to only move forward. Okay, I think its granularity is a second or maybe a little. It's more like it's meant to be a clock which is always on, even, and so if you power up the system and come back on, it's still going to maintain its previous state. So you're not going to be able to turn it back. So TPM provides all of that, and I think enclaves like Apple's and all are a lot more. So built on top of this TPM is the concept of platform integrity. So the idea is if anyone tampers with the platform, I should be able to detect it. If anyone tampers with, if the operating system is not the right one, it will fail to boot. Okay, so like someone goes and messes with the operating system, then the system should fail to boot. If it's an application which is not validated, it should refuse to run the application. I'm sure those of you who have Macs, I'm sure you have faced like when you attempt to install it, asks like whether it's from an authorized developer or not. So there is a whole certificate mechanism and all that it's using, but ultimately it all traces it down to that TPM is the root of trust. TPM validates that the bootloader is okay. Once we know that the bootloader is okay, then the bootloader validates that the OS is okay. And then once we have the OS verified, then the OS in turn verifies that the application is okay. So this chain kind of builds up. So so first stage bootloader, second stage bootloader, OS, apps, they kind of form a chain, but deep down, kind of all of it is tracing its trust back to the TPM or the secure enclave or whatnot, together with the signatures, that it is signed by some trusted entity, like let's say Apple in case of iPhones. So that's kind of the structure. So modern devices are built around that concept. Unfortunately, embedded devices still haven't seen this stuff yet, although you could use TPMs, but honestly at this point TPM, while I'm using that as an example, think of it more as a conceptual example, because TPM largely is viewed as having failed. I think more a reflection of what happened in the PC industry, but the concept itself of having the trusted enclaves and all these kind of ideas is there in all your iPhones and all your Android phones and all your Macs, and I imagine all your modern laptops also. So that whole concept sort of exists. So platform integrity, disk encryption, it gets used out there, protection from password, all sort of other uses, DRMs I mentioned, and also at their heart, that piece of hardware is helping there. Now, having said that, the reason I said TPM had issues and all, so remember TPMs were designed as an off-chip thing. On the PC motherboard, it talks to the main processor. So there are all those traces that exist on the motherboard, and of course you can probe them with oscilloscopes and digital analyzers and whatnot. So attacks happen by examining that traffic. So you cannot go inside the TPM. These are tamper-proof chips. Most people don't have access to things which can examine bits in flight on the circuit. So here, kind of the most obvious way of attack is going after and prying on the buses. So when TPMs were still early on, people showed that they could attack it this way. So Black Hat, which is one of the major security conferences, this particular person kind of showed that they could do it. Differential power analysis attacks have been done. So apparently Edward Snowden in his sort of reveals had that internally the US agencies had been able to mount these kind of attacks against TPMs. There are also software vulnerabilities. TPMs are pieces of software, and of course they have bugs, and so that's another issue. So anyway, so these kind of things. The other thing is also, once something inside the TPM, remember TPM is designed to be protective, so you can't update it, right? I mean, if you had a backdoor to update the stuff inside the TPM, then the whole purpose gets defeated. So for example, some stuff which, some vulnerability in the iPhones, I think until iPhone 9 or 10 or whatever has been found, it can be traced back to an issue with the bootloader, which is signed by the TPM, and so you can't, the stuff is burnt onto the chip basically, so you can't update it at this point. So one has to be super careful that that the stuff which go, if you have any problem in the TPM or the T level, then you have to live with it. Okay, there's no easy way around it. So TPM and those modern instantiations, T's, TPMs and I guess secure enclaves. But what we see now is something even more advanced, and something called T's, or trusted execution environment. So let's see what they are. So that's yet more advanced level of hardware support for security. So as I mentioned very early on in the lecture, processors provide this multiple privilege levels of software. So you have apps and you have operating system code. Operating system code is more privileged. The apps are less privileged. And in case of Intel processors, these privileged modes are referred to as rings. So there are several rings, but essentially think of it as this runs at ring 1, and I think apps run on ring 3 in commonly on Intel processors. Okay, there is a ring 0, which I think is a microcode level, but be what it may, there are multiple levels. Sometimes there is 2 levels. And what happens is that there are certain things you can do in the privileged code, but you can't do in the app code. So, for example, access to I/O, or for example, doing a context switch, those kind of things. You can't, like this app cannot on its own sort of switch to another app. It has to be done through the privileged code, namely the operating system. So typically what happens is that when the app needs to do something which only the OS is allowed to do, then it makes a system call, which is indicated by this arrow. So it basically makes a system call, which is like a, think of it like a function call, but it's more like an interrupt of sort. We're interrupting the OS. We pass it the arguments. The OS then validates, hey, is this app allowed to do it and all, and if so, then it sends back an OK. So that's how the app and the OS interact. Consequence of this is that any interaction between 2 apps that have to take place, that can't. So they are kind of firewalled from each other. So if one app needs to send something to another app, it has to be through the OS. The app writes to the OS, unless the OS deliberately exposes something. So there are concepts like shared memory area, where we can make it visible to be on both the apps, and then they can freely exchange data. So any decision which will let an app mess with anything outside itself has to be done with operating systems knowledge. So essentially, if we trust the OS, then we know that apps cannot mess with each other, and then the hardware isolation makes sure that the apps cannot mess with the OS. And our OS was signed by the bootloader. Bootloader was signed by the TPM or some equivalent of the TPM. So we are good to go, right? Everything is safe. Of course, bugs happen. That's where the problem comes in, right? There's bugs abound in the OS and everything. But leaving aside that, it's a very nice architecture, right? We trust the hardware. Hardware results in a certified bootloader. Bootloader results in a certified OS, and then OS makes use of these privilege modes to kind of be totally protected. So the problem that happens is that what if there is a malicious app, and that malicious app somehow exploits some bug to then gain control, increase its privilege, so that it's able to then run with the privilege of the OS. And once that happens, then since this is a privilege mode, then it can mess with the other apps also, right? So now you're faced with the situation that if you are an app handling sensitive data, and knowing that you are living in this reality that bugs happen and whatnot, then you cannot trust the OS. So our normal model is OS is trusted, and that sort of takes, an app can trust it, so app trusts the OS will keep everything. But in this scenario where a malicious app has affected the OS, then I can no longer trust the app, and yet we are handling, let's say, some sensitive sensor data and all. That's one scenario. Can you think of another scenario where you can't trust the OS? Nothing tricky to it. I mean, it's a simple question. It's not your computer, right? I mean, when you're running it on a cloud service or something, right? So again, you're running on Amazon, for all we know, may have compromised its Linux images and is systematically siphoning data, for example. Okay. So you can't trust when you are outsourcing computation, and you can't trust when knowing fully well that operating systems have bugs and all, right? So for both these reasons, it is important that if you are if you're writing an app which is handling sensitive data, then you don't take it for granted that OS is trusted, even though the system designers have kind of done quite a bit to kind of create that whole chain of trust in making things that the OS has not been tampered with and all. Okay, so yeah, this is just further on that once a malicious app exists, then the isolation gets compromised. So these trusted execution enclaves or secure enclaves, a variety of names, are really an effort to address that issue. That how can an app safely handle private data even if operating system has been compromised. So you could, in a sense, currently, in a sense, the model looks like the following: that an app basically trusts the operating system, it trusts the virtual memory manager and or virtual machine manager, which is underneath, and that's the model. Instead of that, what we want to do is we want to say that the app only has to trust the hardware, and OS can be compromised, hypervisor, which is managing the operating system, can be compromised. I only depend upon the hardware, okay? And ultimately, I mean, that's in a way the best you could do, because if you don't even trust the hardware, then really there is no recourse out. You can't create trust out of thin air, so there is something that you got to trust. So these Ts or secure hardware enclaves in all are, so the most famous one of its type is the one on Intel processors, and it's called SGX. And the idea is that it lets an application run while protecting itself from being snooped upon by the operating system. So normally the operating system can readily examine the entire memory of an application. It can lie. An application may request open file X and tell me its contents, but the operating system can give it bogus contents and all, right? So the OS can basically do arbitrary stuff. So here what you want to make sure is that the OS cannot tamper with the execution in the sense of doing something else that I didn't intend, and the OS cannot look into the memory. So in this case, then the attack surface is the smallest possible that you can imagine, which is app plus the processor, namely hardware nickel. We also have to make sure that the processor is a genuine processor, right? I mean, you could theory imagine that I'm running my code on a supposed Intel processor on AWS, but what Amazon has done is they've implemented a clone of an i86 processor on an FPGA or their own chip and is running on it and then stealing away my secrets, right? So how would you take care of that? How would you make sure that you're running on a genuine Intel processor? You understand the problem, right? I mean, it can, the cloud service provider can basically give you a fake part and executes all the instructions and all, but silently behind the scene it is siphoning away data. So how can you prevent that? Right. So some Intel has to put something using public-private key crypto so that I can verify by comparing against the public data that Intel has published that it was indeed signed by Intel, right? So the hardware needs to be signed. Okay. So part of the enclave story is that the hardware is signed by Intel, so we can verify that, and then we trust it, and it has mechanisms, and assuming Intel is competent, the mechanism, that hardware mechanism is implemented correctly, which will then allow us this ability that I don't have to trust the OS. I can run inside this bubble knowing fully well that the OS cannot peek into my data structures, okay? And that when I run an instruction, OS can stop me from running it, but OS cannot run something else. Okay, that's the important distinction. OS still has control over the processor, so OS can refuse to schedule you application. So your application may have what is called as denial of service. but the integrity of the application is not tampered with. One other big caveat, and this is some work that has gone on in my group, SGX, for example, only cares about the value of the data. It doesn't care about the timing of the data. So OS can still mess with, for example, you ask at what time it is, and the OS can falsify the value. So those kind of things are out of bounds for this model. But any computation, if you ask it to do add, it will be an add. And by the way, the operands cannot be seen by the OS. So that's kind of the model. Okay, so so how does it work? Well, in this case, so what we have is kind of our usual operating system, which is privileged, which normally has full access to the entire memory of an application. It can do anything. It can emulate an instruction. It can do arbitrary stuff, right? And then we have this application. What we will do is we build the app. We think of the app as two parts. Sorry for my bad choice of color, but it's a untrusted app and trusted app. There are two boxes out here, but you think of your application as two parts. One is kind of a normal untrusted part of the app, and the other one is a trusted part of the app. And this trusted part of the app we are going to run inside the enclave. So the idea is that Intel provides an instruction which lets you create an enclave. Okay, so essentially an application can take and put its trusted part inside this enclave, and the result of that is that it is then placed in trusted memory. So there is a region of memory on Intel processors. When they are locked inside an enclave, they are basically encrypted, and they are encrypted using a key that the OS doesn't know anything about. Okay, so essentially at the hardware level, we have now put things inside a lockbox. It's still your regular DRAM, but these are encrypted pages managed by a mechanism outside the OS. So the app runs and creates enclave, and that enclave is put into this trusted memory. So what happens now is that the code which is running inside this enclave, it basically sees the data in the clear, so it has full access to the data. But if anything which is running outside, even the OS, if they were to go to that memory address, they will see gibberish because it's all okay. So external access to the data is denied via encryption. So create the enclave, the hardware does it, and then you can call trusted functions. So like for example, let's say my untrusted part can ask this function inside the enclave to do some service, like fetch some data from a private database and compute something about whether, I don't know, some disease exists or whatnot and all, and send the result. And we can be assured that this stuff has been done, both it has not been tampered with, and is also information is not leaked. So you could imagine now safely outsourcing stuff to the cloud, where what you will do is you will run stuff inside an enclave on the processor at the Amazon end. So so function returns, you get the value, but everything inside the enclave is totally kept in the secret. So this SGX programming thing, I mean, Intel provides a lot of support and all. What's happening is, I'll pick up this again sort of next time, but Intel processors have microcode, so you can almost think of it as at the silicon level, there is a deeper down processor, okay, and a corresponding operating system and all, which is under the hardware, okay. It's like kind of below the most privileged level, which is where all this magic is happening. So this creation of enclaves and all this kind of stuff is being handled by microcode that Intel writes, and of course they maintain all the crypto material and all stuff out there. So at our level, when we are writing these things, there are function calls and instructions and all for you to create enclave and kind of do various kind of things. You can think of as a enclave as data structures plus code, one locked up via encryption and with very well-defined access points to it. Now, having said that, people are pushing this thing quite a bit in many ways. So now you have entire lightweight operating systems or pruned down version of libc and all running inside the enclave, so that you can do a lot of stuff inside the enclave, which normally would have a hard time fitting in. Some constraints: enclaves take time to create and destroy. So you can't simply every function call create an enclave and come back out of it. So the idea is you create and let it run inside. But when it runs at full speed, so that encrypted memory doesn't really cost anything. It's done very, very rapidly. So that's one thing. The other thing is that the memory size of enclaves is limited. So you can't simply say, hey, run kind of a huge part inside the enclave. And that's a couple of one very good reason behind it is the following: if you put large amount of code inside the enclave, then you are taking risk anyway. Your goal should be to take small pieces of your application which you can truly trust and put them inside the enclave. If you kind of put complicated stuff, then complicated stuff will have bugs and all, and then you will again have problems. So we're going to pick this one up, but this has been one of the coolest technologies in recent years from the security point of view. Okay, so see you guys on Thursday.